want to do assign to those two western cities. Draw a tree diagram to show the possible selection plans. Use the product rule to indicate the number of possible plans you could have. Which pairings might you, how many different pairings can you come up with? What would the product rule tell you about that? Suppose that each of the selection plans is equally likely. Then what is the probability that city E is selected? All right, so again, you can go to the Learning Checkpoint, Probability Learning Checkpoint PowerPoint presentation out on the Blackboard to see the solution to that. Another Learning Checkpoint, another example to work through. 5 motors numbered 1 through 5 are available for use. Motor number 2 is defective. Motors 1 and 2 come from supplier 1, and motors 3, 4, and 5 come from supplier 2. Suppose that 2 motors are selected for use on a particular day. Let A denote the event that the defective motor is selected, and let B denote the event that at least one motor comes from supplier 1. So first, draw a tree diagram of all the possible experiment outcomes. Okay. Again, 5 motors are available for use and motor number 2. And suppose 2 motors are selected for use on a particular day. So you're picking the first motor, then you're going to pick another motor. On each of those, you're going to draw, so you're drawing a tree diagram associated with that picking. Use the product rule to indicate the number of possible outcomes. Find the probability of A, and that the event defined as the defective motor is selected, and find the probability of B, to note the event that at least one of the motor comes from supplier 1. Okay, so that's a couple of different counting. How do you count, come up with how many different possible outcomes there are, or how many different possible outcomes are associated with a particular event? Let's move on to looking at permutations. And before we get to permutations, let's go back. You may have had this. I'm not sure what point in your schooling you might have heard or seen this, but factorials as a mathematical definition. For any positive integer m factorial, denoted by m and then the exclamation point, is defined to be the product of the first m positive integers. So m factorial. So I just think about it. 5 factorial would be 5 times 4 times 3 times 2 times 1. 10 factorial. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah, say that one. Not going to dare say what is 100 factorial. So that is what a general definition of a factorial is. Rules, 0 factorial is always equal to 1. And m factorial is always equal to m times m minus 1 factorial. So 5 factorial is equal to 5 times 4 factorial, because 4 factorial is 4 times 3 times 2 times 1. So that is a general definition of factorial. And a permutation. A permutation is any ordered sequence or arrangement of k objects taken from a set of n distinct objects. So that again, you can take a subset, right? You have n distinct objects, and you're going to pick k of them. So I have 5 kids, and I'm going to pick 3 of them. I have 10 facilities, I have 10 factories, and I'm going to make a visit to 2 of them. And in a permutation, order matters. I care whether I go to factory number 1 and then factory number 2, as opposed to I just care whether I go to factory 1 or 2, doesn't matter which order. In a permutation, we care about what order we go in. So a permutation, taking k objects taken from a set of n distinct objects. And what is that equal to? The number of permutations of size k that can be constructed from n distinct objects is denoted as p, and then in front of that would be n, and after it would be k, the number of objects you're picking. So n to pick from, k is how many you are picking, and that's going to be equal to n times n minus 1 times n minus 2, and then all the way as defined here. So another way to look at it is probably the one that you see more often on calculators and in general computational. N factorial, the number of distinct items that you're picking from, divided by n minus k, however many you're picking, what's left over of that you're not picking. So let me move to an example. From among 10 employees, there are to be selected to travel to 3 out of, 3 are to be selected to travel to 3 out-of-town plants, A, B, and C, 1 to each plant. Since the plants are located in different cities, the order in which employees are assigned to the plants is an important consideration. How many ways can the assignments be made? Okay, and so you think there's 10 employees. Employee number 1, and you can put a name to all these people, Jack, Jill, whatever, Robert, whatever, 10 different people, 10 different employees, right? And you want to know the different ways that you could pick 3 of those out to go visit each of these specific plants. And you care who's going to which plant. So how many different ways can you pick those 3 people from the 10, and you care about the order? And so how do you calculate that? That's going to be, you're picking from 10 employees, so that's 10 factorial. And n minus k is 10 minus 3 factorial. And so if you were to look at that, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And if I divide that by 7 factorial, right, which is 10 minus 3, what happens is what's left of the top part is just the 10 times the 9 times the 8. There's 720 different ways to pick 3 employees when the order matters. When I say the order matters, that means that if I look at my employees and say employee 1, employee 2, employee 3, if they actually have unique things, then what I care about is how many different ways can I pick employee 1, then 2, then 3, and employee 2 and 3 and 4, employee 1 and 3 and 4, employee 1, 4 and 5. All of those different triplets with the specific order, there's 720 different ways to do that. And that's what this is telling us, is permutation. Okay. Textbook exercise associated with this, take a pause, go solve that. And again, the main thing is you're using this formula of the permutation, n factorial, the number of distinct objects that you're picking from, divided by n minus k factorial. And that'll help you figure out how to calculate the permutation. Order matters. And again, just to be sure we're on the same page, we say order matters, going back to this example, employee 1, then 2, then 3. Okay, that's my one particular triplet, one of these 720 different ways. That is different. I consider that different than saying employee 3, employee 2, employee 1. Those are counted as 2 different triplets because in the first one, I have employee 1 going to plant A, employee 2 going to plant B, employee 3 going to plant C. And I care about which plants they're going to. So employee 3, 2, 1, employee 3 is going to A, employee 2 is still going to B, and employee 1 is going to plant C. Those are considered 2 different arrangements for where I'm sending employees. Okay, so permutations and combinations. And again, just as an additional note, these are experimenting without replacement. When we did the permutations, once we picked an employee to go someplace, that employee could no longer be assigned to the next plant, so to speak. So we're doing it without replacement. Once I draw a distinct item, so to speak, that item has been assigned and can no longer, you can't double up, so to speak. So combinations, let's look at that. It's an unordered subset of size k, taken from a set of n distinct elements. The number of combinations of size k that can be formed from n distinct objects is denoted as you see here, the combinations, n choose k is a way to say this, as a combination. And this is going to be, if you look, that's n factorial over n minus k factorial. And that turns out to be just the permutation, number of permutations divided then by k factorial. And what you end up here with the combinations, n choose k, is the number of permutations divided by however many items your subset that you're selecting, k factorial. Okay. Think of it this way. So I just mentioned the example of employee 1, 2, and 3. And that triplet is different than, considered with a permutation, that is considered different than the triplet of employee 3, 2, 1. Okay. What we're doing here, and recall that example, we had 720 different ways of getting that ordered triplet. What we're doing is taking that 720 and slimming it down to say, you know what, I don't care who goes to which plant. I just care that I've picked these 3 employees, 1, 2, and 3. I don't care which one. I don't care whether it's 1, 2, 3, 3, 2, 1, 2, 1, 3, 3, 3, 1, 2, whatever. I don't care about which plants they're going to. I just care that those are the 3 particular people I've picked. So what this is doing is netting out, so to speak, the ordering aspect of a permutation by dividing by k factorial. So here we go. Back to the example. So among the 10 employees, 3 are to be selected to travel to a plant, period. Don't care whether it's plant A, B, or C. How many different ways can selection be made? So we had the 720, that's the 10 times 9 times 8. And now we're going to divide by 3 factorial, and this is kind of flipped actually. It should say 3 times 2 times 1, because that's the definition of 3 factorial. And now we have 120 different ways, 120 different triplets that I could pick from 10 distinct employees. And again, this is, they say without, the terminology is it's without replacement, because once I've picked, let's say, employee number 1, that employee can't go to 2 plants. It can only go to 1 plant. So I'm picking it out of the 10 and kind of like putting that employee aside. Okay, you're on the other side of the line here. You're going. Now I have 9 to pick from. Okay, out of those 9, and I have that's actually, so that's where we're coming from with regard to without replacement. Okay, learning checkpoint number 5. How many possible 5-card hands drawn from a deck of 52 cards? Don't care about the order. How many possible 5-card hands are all spades? If each 5-card hand has the same probability, what is the probability of an all-spade hand? Okay, so this last one, I'll just give you a heads up. What you've done effectively is figured out N, the possible 5-card hands, as the first bullet point. How many different outcomes are there? How many different 5-card hands are possible? The second one is N sub A being the event that I get all spades. How many possible ways are there for me to get that? And then I'm going to figure out the last one, which is the probability of an all-spade hand is N sub A divided by N. And so you go over to the learning checkpoint slides, you'll find a solution to that question, those questions. Okay, that wraps up this session, and we will see you next time around for the independence and fundamental rules.